Welcome to the fifth lecture from chapter number 7. We are studying VLSI design, and in this lecture we are going to study transient analysis of CMOS NOT. In our previous lectures we have been studying DC analysis, but in this lecture we will study transient analysis. So what's the difference? In DC analysis, while we perform DC analysis of a circuit, of a digital circuit, we apply the full range of voltages between logic 0 and logic 1 gradually, and we note the output, and finally we plot a curve between the input and the output, and we call it VTC. VTC stands for voltage transfer characteristics. Right. In transient analysis, the input switches quickly between logic 0 and logic 1, and of course we note the output, and we note the output like this. Suppose we have this NOT and the input is varied like this, the output varies, or it responds to the changes in the input, but only with some delay. The delay that is caused when the output goes from logic 1 to logic 0, we call it fall time delay, TF. Why TF? This F stands for fall time. Why TF? Because the output is falling from logic 1 to logic 0. In contrast to this, when the output goes from logic 0 to logic 1, the delay caused during this transition, we call it TR, where R stands for rise. So this delay is due to the reason that we have built-in resistors and capacitors in digital circuits, right? For example, this NOT. So in our previous lectures we have been studying the basic schematic of a CMOS NOT, and we'll continue that, and in this lecture we'll draw an RC, the simplest possible RC switching model for this circuit. This is the basic CMOS NOT, and this, we know this is a PMOS transistor and this is an NMOS transistor. This PMOS transistor can be translated as an RC, as an RC circuit having this CB, the switch VDD, where this RP is the resistance offered by this PMOS and CP is the drain capacitance, and this NMOS can be drawn as R resistor Rn and a drain capacitor Cn, and these switches are controlled by the gate voltage, gate to source voltage. So this is how we can draw an equivalent RC model for this CMOS NOT, and of course this gate has to drive a load that we should call as CL. So this is the RC model of the CMOS NOT, perhaps the simplest RC model for this CMOS NOT for both transistors that we have connected to form a CMOS NOT. Right. Since we have three capacitors in parallel at the output of this circuit, we can write as Cout is Cp, the capacitance of PMOS, the capacitance of NMOS, and the load capacitance CL. Right. So the capacitor, this whole capacitance Cout, charges through Rp when the output is going to be logic 1, and when the output is going to be logic 0, it discharges itself through Rn, because we know when the input is logic 0, this switch is closed and we get and we get this capacitor charge through RP, this equivalent capacitor charge through RP. When the output is logic 1, this closes and we get this whole capacitor, the equivalent capacitor discharge through Rn. So we have two time constants, tau p as Rp, C out, the charging time constant. We have our discharging time constant when the output is going to be logic 0 and the output discharges itself through Rn. Right. So in this lecture we are also going to numerically compute fault time Tf, and in the next lecture we will compute numerically the rise time Tr. So in this lecture we will numerically compute Tf, the fault time. We know that fault time is like this. I have just drawn it in the start of this lecture. That fault time is caused when the output goes from logic 0 VDD to logic 1, and when the input switches quickly from logic 0 to logic 1, the output goes from logic 1 to logic 0 because it is an inverter, but it cannot follow it as quickly as the input is. Therefore there is some delay, and the delay we call as fault time. Traditionally this fault time is like this. Instead of noting from 0 to the time where it is actually 0, or the time when the output was VDD to the time when the output has fallen to 0, we take the time when the output is in fact 0.9, 90% of VDD, to the point where it is 10% of VDD. So we call these 2 points as Tx and Ty on x-axis, on times axis. So traditionally Tf, the fault time, is Ty minus Tx, where Ty is the time when the output has fallen to 10% or 0.1 times VDD, where Tx is the time when the output is 90% of VDD. So between these two values of time, the difference of these two is called Tf. The fault time is the difference of these two values of time, Ty and Tx. Right, and we know, we have studied in linear circuit analysis that the discharge of capacitor can be written as this LCA is linear circuit analysis course, is VDD e to the minus t over tau n, and we know tau n is our NC out. Right, so this is how we can write this expression. This is not a new expression, we studied this in our earlier basic courses of electrical engineering. Right, so we can rearrange terms on this expression to get t on the x-axis and everything else to get t on the left hand side and everything else on the right hand side. So let's start. If we divide this VDD here, this becomes like this, and in order to get rid of this exponent, let's compute log on both sides. And if we compute log of E something, so it cancels and becomes minus t over dn. Right, and we can straight away calculate the value of minus t is multiplying tau n on the other side is tau n log of v of t over VDD. So since there is a minus here, we can have a minus here and can get rid of this minus. Right, and we know that log of A over B is log of A minus log of B. We studied that in class 9, class 10, in school and college. Log of A over B is log of A minus minus log of b. So this can be written as log of v of t minus log of v dt. Therefore, we can also write it as, if you multiply this minus inside, this becomes t is equal to tau n log of v dt minus log of v of t, or it can be written as tau n log of v dt over v of t. So this is a general expression for t for this curve, which is of the shape of a decreasing exponential. Right, so this is t, small t. Now on this curve we have two values of t, dx and dy. Dx is the time where v out is, in fact this is time, and this is v of t. So dx is the time when v of t is 90% of vdd, 0.9 vdd, and dy is the time when it is 10%. So we can write dx as since the time when the v of t is 0.9 vdd, so let's put 0.9 vdd here. So tau n log of vdd over v of t. V of t is 0.9 vdd at this time. So this is tau n log of 1 over 0.9. Since this vdd cancels with this vdd, and dx comes out to be tau n log of 1 over 0.9. Similarly, dy is tau n log of vdd over v of t, and v of t is 0.1 vdd at this time. So dy comes out to be tau n log of 1 over 0.1. So now we have values for dx and dy. Now we are going to calculate df, which is the difference of the two, the fall time delay, the desired value. So what is the expression for df, the fall time delay? df, that is the difference between dy and dx. So dy is tau n dy minus dx log of 1 over 0.1 minus tau n log of 1 over 0.9. So this is tau n taking common, this is, I have missed log here, log of 1 over 0.1 minus log of 1 over 0.9. Once again, this is log of a minus log of b. It can be written as log of a over b. Log of 1 over 0.1 over 1 over 0.9. Tau n log of 1 over 0.1 times, this is reversed when we take it to the numerator, over 1. So this is tau n log of 0.9 over 0.1, or tau n log of 9. So this is df. Log of 9 can also be written as, log of 9 is 2.2. This is 2.2 times tau n, or 2.2 times Rn C out. So if we know the values of Rn and C out, we can calculate the fall time delay df. In the next lecture, we will do some similar calculation to find dr, the rise time delay. Thank you.